basically just shouting.
How does it do it? Why did it stop functioning? I'm like,
Probably better for that paragraph, you didn't answer my meeting.
All right, I think we're good to get started. All right, problem number 1 on today's handout is a type that we already did on Monday. But what we're going to do is do that and then kind of tweak the way we think about it a little bit to give us more power in solving other types of problems. So the value of interest here is what happens as x approaches -3. We know that -3 causes the bottom of the fraction to be 0. And we know from all the graphing stuff we did with rational expressions that there's only one of two things going on at -3. It's either going to be a hole or it's going to be a vertical asymptote. So to determine which of those options, we'll factor the top. The x plus 3's cancel. And the fact that the piece that was causing that restriction at -3 is gone, we know it was a hole. Now, taking that to Monday, if it's a hole, we know the y coordinate of the hole answers the limit question. So we're going to plug in a -3 into the simplified version, and we get -6. So the limit as x approaches -3 for that particular function is -6. Now, we could graph it and then confirm that value graphically. We could set up a table of values in our calculator and confirm it numerically, but we don't need to. We have a set of steps here that will analytically determine what that limit is going to be based on stuff that we know in combination of before break and then on Monday. Everybody okay with that? All right, another thing of note here is it's just a limit as x approaches -3. They didn't ask us from the left, from the right, and then what the final limit is. It turns out that in this little corner of the math world, it's more common to just be asked that third thing. Now, potentially, you may have to consider the left and the right in order to be able to answer it, but we don't need to for this particular problem. For the ones where it is necessary to check is the limit the same from the left and right, it's kind of understood that you do that on your own in order to get that final answer there. Okay, now on to expanding the way we think about this. The bigger picture here is we started with an expression that we were unable to directly substitute -3 into it. What we did was we algebraically manipulated that expression to the point where we could plug a -3 in. Now, we know that works as a strategy because we knew things about this function specifically in terms of how it behaved. But that general idea of regardless of what this looks like, if you can algebraically manipulate it to the point where you can directly substitute that number in, that's a valid strategy. And that's what we're going to work on today. Okay, so on to number 2. This is our function of interest. We're interested in what happens as x approaches 0. 0 cannot be directly substituted into this expression because it causes that expression to be undefined. So what we're going to do is we're going to algebraically manipulate this guy to the point where we can plug in 0. If we can do that, that will answer the limit question. So for this one here, we have a complex rational expression. So our go-to strategy in terms of rewriting this is to multiply through by the common denominator. So all the little denominators inside the big fraction, 1, 1, and x plus 1, the common denominators for those will be the x plus 1. So that times the first fraction on the left here will leave just a 1. Then we have that minus sign, 1 times that. Ultimately, that negative sign will have to distribute through. The bottom, we don't want to multiply that out to see what the top looks like. Now we can clear parentheses up top. Positive 1, negative 1 cancel. So now we're at negative x plus 1. The x's cancel. Negative 1 over x plus 1. All right, now back to the big picture. This was the original expression we started with. We cannot plug 0 directly into that because it causes it to be undefined. So what we did was we algebraically manipulated that guy up to the point where we can plug 0 in. And that is our final answer. And any problems or questions on that one? Okay, so now we're going to take that thought process and revisit something that we talked about in our rational expression unit that we did, revisiting the difference quotient. Okay, that guy as is the difference quotient. And if you recall from back when we were dealing with that, sometimes you're dealing with the general case of an x, sometimes you're dealing with a specific case of a 3. And now what we're going to do is incorporate that into the larger picture, which is the limit as h approaches 0. So we already did this part in the other unit. Now we're going to connect that to limits. So we probably need to spread this out a little bit here. Okay, so we have for number 3, the limit as h approaches 0. And then we'll do the appropriate substitutions here. F of x plus h means we're plugging x plus h into that expression. And subtracting that expression as is. All over h. So back to the bigger thought process we're working on here. We cannot plug 0 into this expression because it causes the bottom of the fraction to be 0, causing it to be undefined. So what we're going to do is we're going to algebraically manipulate this to the point where we can directly substitute the 0 in. So that needs to be FOILed out. Clear those parentheses. And clear these parentheses. I lost something here. Ooh, that plus 1. Here we go. Sorry about that. Copy this one here. Bless you. So we got positive 2x squared, negative 2x squared, positive 1, negative 1. This can divide into two things that remain. And now we can directly substitute in 0 for h. When you're dealing with the limits and a difference quotient where you have an x here as opposed to a specific number, more times than not, you can expect to have x's in your final answer. You're typically going to get an algebraic expression back. If this is a number, like what's going to happen with number 4 instead of an x, then we're going to expect a numerical final answer. And there are special cases where that's not necessarily going to always be true, but in general, that's what you can expect. We okay with that? All right, so number 4 will be another example of limits with the difference quotient. So we have the limit as h approaches 0. And then we'll do our substitution, f of 3 plus h. We're plugging 3 plus h in here. And then subtracting that function evaluated at 3 all over h. So 0 cannot be directly substituted into this expression. So we're going to algebraically manipulate this to the point where 0 can be substituted in. So upper left here, we're going to get 9, 3h and 3h will be 6h plus h squared minus 1, and then 3 squared, 9 minus 8. All over h. 9 minus 1 is 8. 8 minus 8 is 0. Gone, gone, gone. Divide that into both up top. And now we've accomplished that goal, which is our main theme for today. We've algebraically manipulated our original expression to the point where we can directly substitute 0 in for h. And that's our final answer. As far as other methods, just to compare and contrast, numbers 1 and 2, those are pretty traditional. You could put them in your graphing calculator, take a look at the graph, check it graphically. You could set up a table of values, check it numerically. You could do that for number 4 as well, because it's only a single variable, h. The graphical and the numerical approach would not work for number 3 because we have 2 variables, the x's and the h's. So based on the math we know, the only approach we have with number 3 would be to do that analytically. The other ones that we've done so far, we could, if we wanted to, do it graphically. We could, if we wanted to, do it numerically. Okay, good to move on. All right, last 2 problems involving some radicals. Okay, for number 5, I'm going to do a quick pre-example of just a general factoring pattern. If number 5 was, say, x squared minus 10x plus 9 over x minus 1, that would factor into x minus 9, x minus 1 over x minus 1, and they would cancel. And we've done that basic type of factoring. I believe that will be 4,289.6 times. Okay, no surprise there. All right, now, looking at a pattern that occurs here that we can apply to number 5. This exponent in here is understood to be a 1. That exponent is twice this exponent. So if we take a look at, as this appears as part of number 5, what's the exponent understood to be if it's root x? 1/2. 1 is twice 1/2. So the same basic factoring pattern we did here, we can do here. So when we put our x and x here and here, we're going to be using that exponent that's in the middle, or half that exponent. Either way you want to think about it, takes you to the same place. 1/2, 1/2. Minus 9 minus 1. X to the 1/2 minus 1 on the bottom. They cancel. Putting it back in the radical form. So our original problem here we're interested in what happens as x approaches 1. 1 causes the bottom of that fraction to be 0. So, big theme for today. Can we algebraically manipulate this to the point where we can plug 1 in? So extending this basic factoring into something that contains some radicals, something like that I don't think we've seen before, we can algebraically manipulate this into the point where that can have a direct substitution of 0. Oh, it's not 0. 1, sorry. 1. So it'll be the square root of 1 minus 9. 1 minus 9 is -8. That's our final answer. This expression here is a single variable, so it is an option to graph it on your calculator. It is an option to do it numerically. Yes?
Let's just say for like, say the limit was like negative, and there was a negative number in that square root. Would that be like undefined or just not like?
Yeah, so then it would be something, we'd be outside the original domain of the function. So if it's outside the original domain, I guess you'd be answering with it doesn't exist. You can't take a limit on a part of the graph where the limit, say that again. You can't take the limit on a part of the graph where there is no graph. That's not something that would be asked of you on purpose.
Yeah.
I'm thinking that would be like a typo if that happened. That's a good question, though. I didn't think of that as a possible thing there.
Instead of turning the radicals into exponents, can't you just square everything to get one of them? Or is it easier to turn them into?
Well, the squaring everything, if it's an equation, is a fair game thing. If it was something equal to something, then it's fair game to square both sides. But if it's just an expression, then you're not allowed to just square an expression without it being part of an equation.
Okay, so since it's not equal.
Right. All right, so one possibility of dealing with a limits problem that involves radicals would be something like number 5. The other possibility that we're going to be examining is something like number 6, and the one that's like number 6 is actually a lot more common in the calculus world of having this occur. All right, as a quick little pre-example leading up to number 6. If you had something like 2 over 3 plus root 5, and you're in the corner of the math world where you can't have radicals in the bottom of the fraction, what you would do is you would be multiplying the top and bottom of that fraction by the conjugate of that binomial. And multiplying the 3 plus root 5 by 3 minus root 5 would clear out radicals in the bottom, and it would rationalize the denominator. Now, our purpose of doing that here is to accomplish what I just said, to rationalize the denominator. We don't want radicals in the bottom. The bigger picture that can be done by this is the fact of it algebraically manipulates it to look different than what you started with. So that idea, now looking at number 6. We cannot directly substitute 0 into this expression because it causes the fraction to be undefined. So what we want to do is algebraically manipulate this in some way to get it to the point where we can plug in 0. So the way that we're going to do that is by multiplying the top and bottom by the conjugate of the top. Now, what it's actually going to do is going to clear out the radical in the top. We don't really care about, like, is there a radical in the top or is there a radical in the bottom? What we care about is making it look different. All we need to do is get it to the point where we can plug in a 0 directly. That's our goal here. So if it happens to rationalize the top or it happens to rationalize the bottom, well, whoopee, who cares? It's making it look different is the key thing that we're going to focus on here. Okay, so up top, it's a binomial times its conjugate. When we multiply the firsts, a radical times itself, the radicals cancel, x plus 1. We know the outer inner will cancel, the positive radical, negative radical, and then we get a minus 1 for multiplying the last together. Okay, the bottom, we're not going to do anything with that just yet. Up top, Positive 1, negative 1 cancel. So now that we're x over x and then that binomial. That cancels with that. Left with 1 over that binomial. And now we can go back to the bigger picture. We're interested the limit as x approaches 0. So this was the original expression we started with. 0 cannot be directly substituted into that. So what we did was algebraically manipulated it to get it to here. Now we can plug in 0. That algebraic manipulation happened to have rationalized the numerator. Who cares? But that's what it did. The more important thing is it got us to the point where we can plug in 0. So 0 plus 1 is 1. Square root of 1 is 1. 1 plus 1 is 2. 1/2. That's our final answer. Yes.
So like for the complex, or it's just called the conjugate, right? Yeah. So for the conjugate, in like the 3 example, we did 2 over 3 plus root 5. Say that was a -3. That sign wouldn't change.
Yeah, the front sign stays the same. It's only the middle one that changes.
It's only.
Yep. All right. Any other questions on any of these? Yes.
Can you show 3 again?
3?
Yeah.
Like going over it again?
I just need to
I mean, oh, just like show it up here.
Yeah.
Okay. All right, while she copies that down, I'll just give the run through of what the plan is for the rest of the week. Tomorrow is going to be a review worksheet. There'll be a few minor variations that are minor compared to what we've done so far, but for the most part, most of tomorrow should be review. Quiz on this stuff is going to be Friday. It'll be for those of you that are in person, in class, on Chromebooks, at home. It'll be the regular at-home drill that we've been doing for a while. Our in-class group is bigger and growing each day, it seems. There may be an issue in terms of the number of Chromebooks. So if you guys have your own device, please bring it. It would make things a little bit easier in terms of potential numbers with Chromebooks. And that's the plan of where we're going. All right, you guys at home, if you're all good with this stuff, you can leave Google Meet. Otherwise, stay on and ask whatever questions you need to. All right, for you guys, there's still over 15 minutes left. If you want to get a jump on tonight's homework, I have a textbook here if you want to take a picture of the pages. Ava, are you good with this now?
No, I'm good.
Okay.
Yeah.
Yes, you can.
Can I borrow the stapler?
Yes.
How much did you
It's not easy to check the average, you know, you